Hey folks, I've got a Newton's second law example involving the Atwood machine, a classic physics example. And if you need a minute, go ahead and pause the video and write down the givens and draw the situation. I'll explain the situation here. You've got a pulley with a string hanging over it. You've got an M1 and M2 hanging from the pulley. You have a spring scale here. That's going to measure that force. And it's all hanging from the ceiling. And we're going to use numbers eventually on this. M1 is 5 kilograms and M2 is 8 kilograms. And we're going to determine the acceleration of the system, the tension in the string, and the force that the scale reads. So again, if you need a second to pause the video and copy all that down, now would be a great time. All right. So I'm going to start by doing this in variable form in terms of M1, M2. And then we'll throw numbers in just to give you a flavor for how this works. Now, before we start doing the video, or before we start doing the problem, some things to think about. Which mass will have the greater acceleration? M1, that's 5 kilograms, or M2, that's 8 kilograms? Trick question. They're attached by a string. They're going to have the same magnitude of acceleration. One difference in their accelerations, though, is that M1 is going to accelerate up and M2 is going to accelerate down. When you have a system that has multiple pieces to it that are moving in different directions, but they're attached, their accelerations are related, you're going to pick a direction for the acceleration for the system. And for this one, since M2 is bigger than M1, I'm going to say this way is positive, so clockwise, okay? So that's the first thing, is the accelerations will be the same size, and we're going to have a system direction that's positive, okay? Now, the next question is, how many things are moving? Well, hopefully you said 3. You got an M1, you got an M2, and you got a pulley. Now, for this system, we're going to pretend that the pulley is massless and frictionless, okay? Now, that's not realistic, okay? But eventually, okay, we're going to talk about adding mass and friction to the pulley, and that gets a little more exciting. But this is what we call a first order approximation. If the masses are relatively big and the pulley is relatively small, then the answers we get here will be pretty close to what they should be, okay? Now, for the system, we've got 3 things moving, so we're going to draw 3 FBDs. Now, I'll do that here. Let's start with M1. Okay, what forces act on? Oh, when you draw your FBD, make sure you put which direction's positive. First, for this little guy, up is positive, okay? What forces act on him? Well, you got gravity, which is M1G. I'll just go ahead and write that in. It's FG is M1G. And you have the tension, okay? Now, by the way, since the pulley is massless, we're going to assume that this tension in this string and this tension in this string are the same. Eventually, when we give the pulley some mass, those tensions will not be the same. But for this problem, we'll say they're the same, okay? Now, going back to M1 here, we're going to go ahead and write Newton's second law out. And for all these, I'm using net force equals ma, okay? And I'm going to, net force in the positive direction in this case. So in this guy, this would be T minus M1G equals M1A. And there's your equation of motion for that guy. Now, how about M2? Okay, so here's M2, okay? The FBD looks very, very similar. You've got tension acting up, the same amount of tension. You've got M2G acting down, but the difference is our positive direction is down, okay? So the equation will look a little different. You're going to have M2G minus T equals M2A, okay? Now, there's a third object, the pulley, and we're going to draw an FBD of that shortly. But I'm going to start by working with these 2 equations here, okay? So what I typically do on a problem like this is I tell students to add the equations together, okay? So I'm going to take this equation plus this equation and get a resulting equation. And you'll notice that when you do that, you have a positive T here and a negative T there, so the tensions cancel out. So you get m2g minus m1g equals m2a plus m1a, okay? And then if you were to solve for a, first of all, I would factor the g out of this, and so you end up with m2 minus m1 times g divided by m2 plus m1, okay? Now, a tendency will be for folks to memorize this equation. Please don't do that. It's much, much, much more important that you understand how to get there, okay? Now we have that equation, and I do have numbers, so I'll go ahead and plug those in now. So M2 was 8, M1 was 5, G is 9.8, and then we have 8 plus 5. And if you plug and chug those in your calculator, you get about 2.26 meters per second, okay? Now, before we find the tensions, let's talk the tension in the string. Let's talk generally for a second. Just for fun, I'm going to label the two weights on here. So this is FG1, which would be mg, which would be 5 times 9.8, which would be 49 newtons. And this guy would be FG2, which would be 8 times 9.8, which would be, if I do that in my calculator, I get, hold on one second, I wrote that out somewhere. I guess I'll have to do that. 8 times 9.8, I get 78.4 newtons, okay? Now, if I then go to ask, hey, what's the spring scale measure? A common error that people will make is they'll say, oh, it's 49 plus 78.4. And if you take 49 plus 78.4, you get 127.4. So will the spring scale read 127.4? Well, it turns out, no, it will not say 127.4 newtons, okay? So what will it say, all right? Well, first of all, in order to figure out what the spring scale is going to say, we have to go back and find the tension. Now, something about the tension. There is a range for the tension, okay? The left-hand block is accelerating up. So the tension has to be greater than 49 newtons. The right-hand block, the M2, is accelerating down, which means the tension has to be less than 78.4 newtons. So whatever tension I get, it better be between 49 and 78.4, okay? Well, it's real easy to do. All you do is take this 2.26 acceleration and you plug it back into either equation, okay? So either the first or second one. I'll do the second one because I can see it in the screen there. And if you plug in 2.26 right here and you solve for tension, I'll save you the effort, you'll get about 60.3 newtons, okay? Which is indeed between 49 and 78.4, okay? Now, having said that, now we're going to figure out what the spring scale reads. So I'm going to draw an FBD of the pulley. What forces act on the pulley? Well, the spring scale, okay? You have the tension pulling down on the left and the tension pulling down on the right, same amount, 60.3 newtons. And we said this is an ideal pulley. It's massless and frictionless, and that'd be great if we had one of those. Now later on we'll throw some mass and friction in there, but for now we're saying massless and frictionless. That means that this force has to equal those two. So the force of the spring scale has to be equal to 2T. And we know our tension is 60.3. So force of the spring scale has to be 120, approximately 0.6 newtons, okay? Which is less than the 127, the weight of the system, okay? Now, another note about that. It should be less, because if you really think about it hard here, you have more mass accelerating downward than you have accelerating upward. So on the system, the overall net force should be down because you got more mass accelerating down. So when we do, we have a total of 127 newtons of force acting down, and we have approximately 120.6 newtons acting up. So the overall net force is down on our system, and we have more mass accelerating down than we have accelerating up. Well, I hope that example was helpful. It's a classic Atwood example, and have a good one.